All right, welcome. We're discussing a beautiful theorem called Viviani's theorem. And it's a beautiful theorem in geometry. So I think it's time to introduce what the theorem talks about. So here you can probably see that we have an equilateral triangle. We have a point inside it. And for those who don't know what an equilateral triangle is, an equilateral triangle has three equal sides. So AB equals BC equals CA. So what I could do here is if this common length is equal to S, then I could simply just label all these sides as S. And an arbitrary point means that I could just pick any point inside the triangle. Just like imagine you take a finger, you have a triangle on like a whiteboard, and then you just like you blindly pick a point inside the equilateral triangle, and that's your point P. So you pick any point, it could be arbitrary. So let's see what is so special about this configuration. So what I'm going to do is I'm going to draw the distances from the point P to each of the sides. So P to BC is H1, P to BC is H1, P to AB is H3, P to AC is H2. And then I'm going to draw a height of the triangle, so from A to BC. Now, you'll see why this is so important in a second, why it's so special about it. But I want to ask you a question, like, what is so special about this configuration? There must be something so special about it. What's the relation between these lengths that I drew? Maybe you could see it. Maybe you can already, you could take a guess at it, at what I'm trying to get at here. But I want you to keep that in mind while we discover what this theorem has to say. So what I'm going to do is I'm going to find the areas of these four triangles right here. So ABP, BPC, CPA, and ABC. And the way that we do that is to the common formula is the area of a triangle is base times height over 2. So how we can use that here is for like APB. I'm going to draw these lengths in. We want to find the area of this highlighted triangle. And we know that the height is H3. We can set the side length as S. So yeah, the side length is S. And then we could find the area of APB. So we have the base is S. So I want to let that be the base. And we also have the height since this is the distance. So it's going to be perpendicular to AB. So that would be the base, the height, divide that by 2, we find the area. And we can do that for the other triangle. So BPC, you have the base as H1, the height is H1, the base is S. For CPA, you have the height as H2 and the base as S. But then for ABC, we have something a little bit different here. We have this line in the middle. That would be our height. And we also have a base here as S. So the area of ABC would be S times H over 2. So a little bit different. But wait, I'm pretty sure that, we take a point inside and we find these three areas. There must be something special about those three triangles. And in fact, there is. Notice that these three triangles, they make up the triangle ABC when you put them together. Because, you can draw in those three lengths. You could find this area here. Notice that they basically make up triangle ABC. That's beautiful. And that gives us this amazing inequality, which then we could just straightly plug in to the formula that we found. So when you plug in these four results that we had earlier, and we plug it into this equality statement, we can notice something very interesting. So notice that when we substitute the values, we end up with this. Notice what happens when I just cancel out the S over 2 in each side. When you cancel out the S over 2, well, the S over 2 is all common, so you can cancel out. You just end up with H3, H1, and H2 on the left-hand side, and then you end up with an H on the right-hand side. So what you end up getting is this beautiful statement where the heights are all equal. So you have H1 plus H2 plus H3 is equal to the height. And that's exactly what Viviani's theorem states. So this is Viviani's theorem. It's a beautiful theorem. Where basically I can formally state it as like if you pick up arbitrary point P in a triangle, well the distances between each of the three sides is equivalent to the height of the entire triangle. And that's really beautiful. So let's see how we can apply this. And we're going to apply this to the 2020 Math Count State Sprint round number 25. I remember taking this in test, didn't solve it, but it was a very beautiful question when I looked at it afterwards. So let's see what it has for us. So we have an equilateral triangle of side length 11. So I'm going to draw on all the sides. And this is exactly what we want, an equilateral triangle. That's the first clue that we want Viviani's theorem. Okay? Now we have 12 last points on each side. Nothing too crazy there. Then we have one last point inside the triangle, randomly selected and labeled point P. So it could be that point. It doesn't have to be. That's just an example. Okay? Now, if you say the distances from each of the sides, so A, B, C. A, B, C are the distances from P to the sides. Oops. A, B, C are the distances from P to the sides A, B, C, AC, and AB, respectively. I want to find the probability that a triangle exists with the side lengths A, B, and C. Okay, beautiful. So, we want to find the probability that a triangle exists between these three sides. But, okay. Well, firstly, we can use Viviani's theorem. So let's just draw on the height. I'm going to do it a different color, actually. Let's draw on the height. Let's say that's H. And then by Viviani's theorem, we know the three distances for the sides, say A, B, C, sum to the height of the triangle. And that's H. Okay? I'm not even going to solve for H. You can if you want, but I'm not going to do it. Not yet. And now, we want to find the probability that a triangle exists. Okay, but remember, the only thing that requires a triangle to exist is a triangle inequality. And what this implies for us is that A has to be less than B plus C, B is less than A plus C, and C is less than B plus A. Okay? So now what I'm going to do is I am going to add I'm going to add A to this side here. I'm going to add B to this side, B here, C here. Okay, but these three lengths, they're all H. So we know that 2A, here, I'm going to say 2A is less than H, 2B is less than H, 2C is less than H. Okay, now let's see how we can use this in the figure. So let's say we have this inequality right here. We know this is H, A is less than H over 2. So just looking at it, right? Well, this H here, right? We have this line H here. And A has to be at most half of that length. So we could just draw on like the perpendicular bisector between these four, we draw on the perpendicular of this orange line. So when you draw the perpendicular bisector, well, it should be somewhat right here, I believe. So this is 1, 2, 3, 4, 5. And then when you add this in, that becomes 5.5. And the same thing here. 1, 2, 3, 4, 5. And then we add in this half here, so 5.5. So yeah, it is the center. That's the perpendicular bisector. We can do this for the other three sides as well. Let me do it right here and right here because, well, we also know that, B is less than H over 2 and C is less than H over 2. That's what allows us to draw on these three lines. So we basically just want to find the probability that P is one of those selected points, right? So here we have a little bit of better diagram for us to visualize. You want to find the probability that P is one of those 4 points. And now with the abilities of Viviani's theorem and the triangle inequality, we were able to narrow this problem down and try to figure out what we want to find a little bit easier. And that's what's great about the method that we're taking, okay? So we want to find the probability. We're not done yet. So we want to find the probability that P is one of the selected points. So probability that P is equal to a green point over the probability of total. Or I should say, actually, this is kind of wrong. We want to find the probability that P is, we want to find the probability that P is green. So probability that P is green is equivalent to the number of total green points over the number of total points, okay? So, well, let's just try to compute the number of total green points. So I'm going to do that in green. We have a row of 5 here. We have a row of 4 here. We have a row of 3 here. We have a row of 2 here. We have a row of 1 here. So the number of green points is just 5 plus 4 plus 3 plus 2 plus 1. That comes out to being 5 times 6 over 2, which is 15. And the reason that is because n plus until 1, so the first n numbers, is equivalent to n times n plus 1 over 2. A great formula that you should try and memorize. Yeah, and maybe you can even try to prove it. And it's a very important theorem that comes up on a lot of problems. So that's something we need to make use of. We don't want to hand calculate it because you'll see in a second that we might get a larger sum. So I'm going to do the next part in blue. I want to find the number of total points here. So we have the green points, that's 15. We want to find the number of total points now. Okay, so the number of, blue points, I guess, or number of total points in the bottom row is 12. Here there's 11, 10, 9, until so on, until we get 1. Okay, and notice that it's 12 lattice points on each side, so there would be 12 here. Okay, not 11. Okay. Okay, I should actually point out, this is a very tricky question, okay? I got tricked by this, actually. So one of the lattice points inside a triangle is randomly selected. So we aren't picking points on the outside of the triangle. It's very tricky with how they do this here because, the points in the problem are also bulleted, which is very tricky. But we just want to find the total number of points inside the triangle. So we want to find 1 until 2 until so on until we get to here at the bottom. Here there's 9. So we want to find 9 plus 8 until 1, which is 9 times 10 over 2 using this amazing formula right here. We have 45. So the probability that a triangle exists, so the number of total points is 45. So the probability that a triangle exists is just the probability of green, which is, well, when you divide these two numbers, you get 1/3. It's a very beautiful answer. So that's a very challenging question, and we made use of all different things from Viviani's triangle equality, the sum of the numbers from some of the first n numbers. Those are all tricks that you need to use to solve a math down state sprint question. But we mainly made use of this Viviani theorem and triangle equality. So beautiful. Now, just to summarize our findings here, in a general case, maybe you see a different question not involving equilateral triangle. Maybe in a more general case, the sum of the distances to the sides from an interior point is independent of the location. So you could pick any polygon. Maybe you want to pick a pentagon, and then you draw the distances. Well, this distance is always going to be constant. Maybe you want to draw like a heptagon. So let's draw that. Not the best, okay? You want to take the distances from each of the sides. These distances are all going to be the same. You can do this for any polygon. Maybe it's not a 5-gon, maybe it's not a 7-gon, maybe it's not an equilateral triangle. Anything that's a regular polygon. Regular means that all the sides are equal and all the lengths are equal. And it equals n times apothem. And the apothem is basically just when you have I'm gonna take an equilateral triangle. You take the center of it, and then you find the distance from each of the sides, well, this is just the apothem. When you take a center, and then from one of the sides, the distance between the center and one of the sides is the apothem. So commonly, I found this in like a hexagon. This would be the apothem. So yeah, that would be the apothem. It's n times the apothem in a regular polygon with n sides, I should say. I don't know why it doesn't say that, but yeah. Awesome. Cool. So hopefully you understood that part. Now let's see what's so special about this hexagon. This is the last thing, so stay with me, but let's see what happens in this hexagon here. So I'm gonna extend. No, that's not a good color. Maybe that. I don't like that one either. Okay, like this. I'm gonna extend each of the sides to meet. Notice something. Notice anything. Keep it in your mind. Maybe you see it already. Okay, I want to figure out anything between these orange length and these blue lengths. So, what do we see? Well, you can extend these lines and notice that it forms two identical equilateral triangles. Probably should have done it in a different color here. So this one, the red triangle, is equivalent or identical to the purple triangle. And so what that means, well, notice you're taking a point P inside both of these equilateral triangles. But by Viviani's theorem, let's say you take the red triangle first. You take the point P, extend the distances. Well, that's just the blue lengths. So the blue, that's not the best. The blue is equal to the height of the equilateral triangle. And the orange length, well, that's just the distances between the other equilateral triangle. So orange is also equal to the height of triangle. So these are the same. So the blue and equals the orange. That's beautiful, beautiful, beautiful thing to notice here in this diagram. And that's just a beautiful property that you can apply Viviani's theorem to all different things, and you can get some beautiful results. So I encourage you to maybe look into this more deeply and see what else you can discover. So yeah, that's it for today's lesson about Viviani's theorem. So hopefully you learned a few things. Maybe you learned how to apply this, apply Viviani's here. Maybe you learned something from this problem and different ways to apply Viviani's here. Maybe just like the proof, and maybe you can apply different parts of the proof to other different things that you see in geometry. So yeah, hopefully you learned a lot from this video.